Today we're going to continue where we left off last time. We were talking about all pairs shortest paths. And remember that we were trying to solve this problem on a graph that was undirected and unweighted. In the last session, we saw two different things. First, we saw that we can compute all pairs distance in better than cubic time. And the algorithm that we had was order n to the power of omega times log n, where n is the number of vertices and omega is the matrix multiplication constant. So we don't know the exact value of omega, but we know that it's at most 2.37 something. So this was the first algorithm that we saw. And then the second algorithm we saw was about finding witnesses in Boolean matrix multiplication. So finding witnesses for A times B, where A and B are Boolean matrices. And we saw that we can solve this one in a similar runtime, n to the power of omega, but then we had log squared of n. And remember what we meant by finding witnesses? Basically, the idea was that if I show C to be A times B, and then if I say that Cij is true, then this means that there should exist some k such that Aik is true and also Ekj is true, right? And this k was called a witness. So in the problem of finding witnesses, we wanted to find some other matrix W such that Wij is 0 if Cij is 0, and it's some number k, the witness k, if Cij is not 0. And we saw a randomized algorithm for this last time. Our randomized algorithm had this runtime, n to the power of omega times log squared n. And we saw that every entry in the witness matrix W is going to be wrong with probability at most 1 over n. So yeah, here we said that every witness is correct with probability more than n minus 1 over n. So it's wrong with probability at most 1 over n. This was the result that we got last time. And this was actually the reason why we had this second log in our runtime. Because we had an algorithm that took only one log in the runtime, but it just gave us a constant probability. And then we would just take that algorithm and repeat it log n times, so that the probability that every witness is incorrect is at most 1 over n. Of course, I can repeat that same algorithm instead of log n times 2 log n times, and then the probability would be at most 1 over n squared. But this is all I need, so I'll just use this. Okay. So these are the things that we have from last time. Now the question is, how does this help us with finding shortest paths? So our setting was that we're given some graph G, and then we can pre-process it. Of course, we pre-process it for distance. And then we were going to have to answer some queries. And each query would just give us 2 vertices, U and V. And we had to output a shortest path from U to V. And we had to answer the queries optimally up to a constant. So we had to make sure that the runtime that we spend on answering each query is proportional to the length of the answer. Okay? Now, so let's just repeat the notation from last time. We had a graph G, and this was given to us by an adjacency matrix N, A, which was N by N. And then from that, we computed a distance matrix D, which is also N by N. And this is this part. But now let's talk about the queries. So let's say I have a query, and let's say the query is giving me 2 vertices U and V. So I want to find the shortest path from U to V. Now, I know the distance from U to V, and I can output that immediately. That's just what I have in this matrix. So DUV, that's fine. But then I have to also find a shortest path. So I want to somehow reduce this problem to the problem of finding witnesses here in Boolean matrix multiplication. So what do I want to do? Let's say I want to start from vertex U, and then maybe I want to go to another vertex W1, then W2, and so on. And then eventually I want to go to vertex V, right? So ideally, what I want to be able to do is to just find this first internal vertex. So I want to define the matrices A and B here in a way that I can just find this internal vertex W as some witness in A times B, because I know how to compute witnesses there. Okay. So what do I know about this W? Or actually, let me call the first vertex maybe something else. Yeah, let me call it K. So I go from vertex U to vertex K, then I go some other paths, and then eventually I get to B. So what property should K have? If I want to find a vertex K like this, what are the properties? Well, of course, the distance from U to K has to be 1, right? And then the distance from K to V has to be the distance from U to V minus 1. Okay, so these are the conditions that I need for K. So I need to find some vertex K such that the distance from U to K is 1, and the distance from K to V is this distance. Actually, let me just give it a name so that I can work with it more easily. So let's say this was T. So the distance from K to V has to be T minus 1. Okay. But I have to somehow turn this into matrix multiplication, Boolean matrix multiplication, right? But let me rewrite what I removed from the Boolean matrix multiplication. So we had that if C is A times B and A and B are Boolean matrices, then Cij is 1 if and only if there is some K such that Aik is 1 and Bkj is 1. Okay, so I know how to find a K like this, but the conditions I have here look a little bit different. So I just have to kind of massage these constraints so that they look like this. Okay, so what can I say if the distance from U to K is 1? What does that mean? That means that there is an edge from U to K. So they are adjacent. So in the adjacency matrix, it would also be 1. So I can say that instead of duk equals 1, I can just say that auk is 1. Okay, but what about this part? Now, in this part, I basically want to know that bkj is 1 or bkv is 1 if and only if dkv is t minus 1. So I can define my matrix V. And let's say that this matrix B is parameterized by this distance. So Bt is also an n by n matrix. And I say that the entry at position uv or ij, uv of this matrix is just going to be kind of like an indicator variable. So it's going to be 1 if the distance is t, and it's going to be 0 otherwise. Okay. So now, so basically this is a matrix that I'm getting from my distance matrix by a simple pass, right? I'm just going over my distance matrix. Whenever I see t, I put 1. Whenever I see anything else, I put 0. So now here, I can just say I multiply my adjacency matrix A by this matrix B. But I want the distance to be t minus 1, so B with parameter t minus 1. Okay? And I can now call this, I can take this matrix multiplication, and then I can apply the algorithm that we saw last time for finding witnesses. So let's say that WT minus 1, or okay, yeah, WT minus 1 is the matrix of witnesses for this multiplication. Okay. Now, if I have this, then basically here what I wrote is the same as saying that this K is the witness at index UV of this matrix, right? So what I have to output is actually quite simple. I just start from U. So I first output U. Then I want the next vertex, which is supposed to be K. And this would just be WT minus 1 of UV. So entry UV of the witness matrix with parameter t minus 1. And then I can just continue this, right? So again, if this was K, then the next one is just going to be WKV with index t minus 2 and so on. And I continue this until I get to. Okay. Now, this is good because whenever I want to do a query, I'm really spending constant time for each part of each number in my output here. So U is just given to me in the query. In order to find the next vertex, I'm just looking into a matrix of witnesses that I had. So that's constant time. And then after I have this, finding the next one is also constant time. But this is assuming what? This is assuming that I have these witness matrices. So I have to somehow compute these witness matrices in my pre-processing phase before doing the queries. But now this is the part where we get into a problem. So finding each one of these witness matrices is going to take n to the power of omega times log squared n. But how many of them do I have? Well, I have one for every possible distance, right? So this is not so great. Now, the amount of time that I'm spending is going to be n to the power of omega plus 1 times some log. And this is worse than n cubed. So can we somehow decide to only compute some of these witness matrices and not all of them? You see, all of our problems are coming from the fact that we're computing n different witness matrices for different distances. So how can I be a little bit smarter about computing this? Okay. So here's what I want you to visualize again. And this is a picture that we've seen many times. So let's say I have U and I have V. And the distance between U and V is T. Okay. Now, this is the multiplication that I'm doing here. So when I'm trying to find this K, of course, I'm trying to find K among the neighbors of U. That's why I'm multiplying A, right? So let's just look at all the neighbors of U. So let's say these are all the neighbors of U. What are the possible distances from these neighbors to V? The distance from each neighbor to V can either be t minus 1 or t plus 1. Right? Because U to V was distance t, so there is one vertex or maybe more that have distance t minus 1 to V and are neighbors of U. And then there are other vertices. It might be that this vertex has a path of length t. That's fine. Or it might be that the shortest path goes through U, and then this vertex will have a distance of t plus 1. But the important point here is that if I have this vertex U, all the possible distances from its neighbors to V are just going to be t minus 1, t, and t plus 1. So when I'm multiplying this thing here, there are only 3 values for this parameter that I should possibly consider, right? And everything else would just become 0 from the point of view of A. So this is what I can do. I can say I just create 3 different matrices B, and this is how I define them. So I say B0 of ij is going to be 1 if the distance from vertex I to vertex j is divisible by 3. Okay? And I'm going to say it's 0 otherwise. Or actually, let me use a more mathematical way of writing this. dj is equivalent to 0 modulo 3. Okay? And similarly, I can define a matrix called B1 and another matrix called B2. And it's again the same. So B1 of ij is 1 if the distance from I to j modulo 3 has a remainder of 1. And B2 of ij is the same thing for remainder 2. Now, instead of this bt minus 1 here in the multiplication, I can just use bt minus 1 mod 3. Right? And everything would work out. Why would everything work out? Why would these 2 things not be too different? Because anyway, when I'm looking for the shortest path from U to V, I'm trying to find this vertex K. And I know that this K, its distance to V, should have a particular remainder when divided by 3. And that's all I need to know. If I find any neighbor of U that has that particular remainder, then I'm sure that that's going to be on the shortest path from U to V. Okay? So this is how we compute only 3 different matrices B. And so finding these witnesses is going to take O(n) to the omega times log squared of n. And I'm doing this 3 times. 3 is just a constant, so the runtime is going to be the same. So putting all of these things together, for the pre-processing, I would first compute all the distances, n omega log n. Then I need to find witnesses for 3 different multiplications. 3 different multiplications of Boolean matrices. And that's going to take n omega log squared n. And okay, now that we have all of these things, let's go back to querying and see how we do the query. So I was assuming that I have these witnesses, and these witnesses are correct when I was doing my query before. But actually, the guarantee that I had for my witness finding algorithm was not that they're going to be always correct. It was that the probability that a particular witness is incorrect is at most 1 over n. Right? So when I want to find the shortest path from U to V, I have to be a little bit more careful. So I first look at the witness matrix at index t minus 1 modulo 3, and then I look at entry UV of that matrix. Now, with a very high probability, with probability at least n minus 1 over n, this entry is correct. And if this entry is correct, I can just print it. But there is also a 1 over n probability that this entry is wrong. So I have to somehow handle that in my query phase as well. Now, first of all, I can easily check whether this entry is correct or not, right? Because if I find this vertex K, I can just check if U has an edge to K, and if the distance from K to V is t minus 1. That's constant time checking. because I already have all of this in my matrices. So I just do a constant time checking, and I figure out if I have the right witness here. If I have the right witness, I'm happy, and I just continue, find the next witness, find the next vertex in this path, and so on. But if I figure out that this is not the correct witness, then I just iterate over all the neighbors of U. So at this point, I'm going to do something that is very inefficient. I'm just going to go over all neighbors of U and figure out which one of them has a distance of t minus 1 to V. Now, even though this is very inefficient, I'm doing it with very low probability. So now I want to compute my expected runtime. So actually, let me do it without writing it. So the expected runtime for just finding one witness, how much time do I need for that? So with probability n minus 1 over n, I get my witness in constant time. With probability 1 over n, I have to go over all the neighbors of U. So I have constant time with probability n minus 1 over n, and I have to, well, in the worst case, U has n neighbors. So I have to check n neighbors, but with probability 1 over n. Okay, but this is again just a constant, right? This is less than or equal to c plus 1. So the expected runtime I have for finding each one of these intermediate vertices is constant. So the total expected runtime is just going to be OT, where T is the actual query, actual distance between the vertices that were queried. And again, this is optimal because now our runtime is basically linear in the size of the output that we have to print. So we can't do better than T. Okay. Yeah, so this is all for the randomized algorithms module of the course. And you will get your first homework after this session. I'm now going to switch to the next module. So our next topic is going to be about parameterized algorithms. Okay. So here's what I want you to think about. Suppose that I give you some problem, and suppose that the problem is NP hard, or let's say it's also in NP. Let's say I have an NP complete problem. So I have a problem, let's call it P, that is NP hard. Now, if my problem is NP hard, as I've told you before, we don't know whether P is equal to NP, but we kind of assume that they're not equal. So assuming that P is not equal to NP, this means that, oh, okay, I shouldn't call my problem P. Let's call my problem L. Okay. So let's say I have a problem L and it's NP hard. Assuming that P is not equal to NP, this means I cannot really find a polynomial time algorithm for L, right? But I just want to be more specific about what's being ruled out here. So assuming P is not the same as NP, we cannot have an algorithm for L cannot have an algorithm A for L, and by this I mean that A decides L, such that all of these constraints are satisfied. Well, what are the constraints that I should have? Well, the first thing is this algorithm has polynomial time. Of course, if my problem is NP-hard, I might be able to find an algorithm for it that uses more than polynomial time. Maybe I can find an exponential time algorithm. So the fact that it's NP-hard is ruling out that it has an algorithm that is polynomial time, but also this algorithm has to be deterministic, right? So again, even though my problem is NP-hard, I might be able to find a randomized algorithm that solves it in polynomial time. So the thing that is being ruled out is that the algorithm is deterministic. What else? Well, if this problem was not necessarily, let's say, a decision problem, but maybe an optimization problem, then I have to say that the algorithm has to be exact, right? So I might have an optimization problem that is NP-hard, but I might be able to find an approximate algorithm for it. And if you think about it, we had one example of this before. There was max-cut, right? Max-cut was an NP-hard problem, but we had an approximation algorithm for it already. And the last condition is that A has to solve every instance of my problem. Okay. So if my problem is NP-hard, then I don't have an algorithm that runs in polynomial time, is deterministic, is exact, and solves all the instances of my problem. But now I can just compromise over any one of these. So the first one is not really the focus of our course here. So I can compromise on polynomial runtime. That's fine. We've already seen a lot of randomized algorithms. Very soon, we will also see some more approximation algorithms. But this is the part that I want to focus on right now. So what happens if I say I don't want to solve every instance of my problem? Maybe I just want to solve some instances that happen in the real world. So it might be that my problem is hard theoretically, but all the real world instances have some nice structure, and that nice structure can be used to find a good algorithm. This is the idea behind parameterized algorithms. Okay. So to be more exact, when I'm talking about a parameterized algorithm, my input is no longer just going to be some string. It's also going to contain a number. So for a normal decision problem, we had some alphabet sigma, and then our input was just some member of sigma star. It was just a string. But now I want to say that my input has a string and it also has some integer. And the idea is that this integer gives me some extra information about my input. And then I don't want to analyze the runtime of my algorithm only based on the length of the input, but also based on this extra integer that I have. Now, this will become very natural very soon. So let me start with an example now. So the most classical example here in parameterized algorithms is the problem of vertex cover. So what's vertex cover? If I give you a graph G, a vertex cover of G is a set of vertices such that every edge has one of its endpoints in the set. Okay, so let's say my input is some graph G, and let's say that I also have some integer K, and the output is that I have to decide if there is some S subset of vertices such that every edge has one of its endpoints in S. So how can I write that? I can say that if I take G and I remove S from G, or if I take G limited to V minus S, then this graph should have no edges. Okay. And of course, I want the size to be small. I want the size to be at most. So let's say, let me just do an example here. Let's say I have this graph. And black like this, okay? So I have this graph and I want to choose some vertices so that they cover all of the edges. So I can choose maybe this one and this one and this one, right? Now, every edge that you consider here has been covered by at least one of the red vertices that I've chosen. Okay, so this is now a vertex cover of size 3 for this graph. Now, the question is that you're given some graph and you're given some integer k, and you have to say if that graph has a vertex cover of size k or smaller. And of course, you can either output the vertex cover itself, or you can say that the problem is just a decision problem. You should just say yes or no. Now, this problem is actually NP complete. And it's not too hard to show it's NP complete. I'll leave it as an exercise for you. But when we say it's NP complete, what do we mean? We mean that we're analyzing the runtime based on the length of the input. But what is the length of the input here? It's how many number of bits do I need to represent this graph and also to represent this integer k. So if my graph has, let's say, n vertices and edges, or n vertices and m edges, then my input size would be n plus m plus 1. Or if you want to be more specific and you want to really count the number of bits, you can say it takes log k bits to write the number k. So then the input size would be n plus m plus log k. Okay? But that's not how I want to analyze the runtime. Instead, I want to use this number k as my parameter, and I want to analyze the runtime based on both n and k. So I want to find an algorithm whose runtime is not just dependent on the size of the input, but also on this extra parameter k that was given to me. Okay. So what algorithm comes to your mind? What is the simplest algorithm that we can have here? Yeah, you can just try every possible combination of k vertices, right? So you want to see if you can take k vertices that cover all the edges? Just try every possibility. Try every subset of k vertices and see if they cover your entire set of edges. So how much time would that take? Well, I have n choose k ways of choosing a subset of size k. And then after I do this, I have to go over every one of my edges and see if it's covered by this subset. So that would be O n choose k times n. Okay. Now, n choose k is almost like n to the power of k. So I can say that I have an algorithm now that takes this runtime, n to the power of k times n. Now, this algorithm is actually kind of good. Here's the thing. Suppose that I tell you that for the use cases that I have in the real world, for the real world instances, I guarantee you that k is going to be small. Maybe I want to use this for some use case where I know that k is at most 10. So in that case, you have a polynomial time algorithm if you're guaranteed that the value of k is small in the input. So you have an algorithm, for example, if k is at most 10, that is taking O n to the power of 10 times n. So even though the problem is NP hard, if this parameter k is small, you can solve it in polynomial time. And This kind of algorithm is usually called an XP algorithm, and XP stands for piecewise polynomial. I don't know how they came up with X there, but XP means piecewise polynomial. So if I want to give you an actual definition, this is the definition. So now that I'm working with parameterized algorithms, I have to define a lot of new things. So I have the same alphabet as before, which is usually 0 and 1 for writing the input. But now my input is going to be some string and some integer. So in other words, if I want to define a language now, my language was supposed to be a set of inputs, right? The set of inputs that are accepted by this algorithm. So now a parameterized language is just some L, but this L is no longer just a subset of sigma star. It's a subset of sigma star times n. So every element in my language has a string and an integer. Okay? Now, with this definition, I can then say that XP is a complexity class, a parameterized complexity class, and some language L is in XP if and only if there exists some algorithm A that solves or decides N and now I have to talk about how much time this A takes. So I want to say the time it takes for the algorithm A to run on an input, but now my input is some string, let's call it X, and some integer, let's call it K. So the time it takes for my algorithm to run on input X with parameter K has to be bounded by some polynomial in terms of X. Okay, so I can say length of X to the power of some constant, I want to say. But the thing is, this constant can actually depend on K. So I can say that it runs in time X to the power of some function of K. Let's call that function G. Okay? So, and again, here I just say there is a function G. So all I'm saying here is that a language is in XP if you can find an algorithm whose runtime looks like this. So it's polynomial in the length of your input, but the degree of the polynomial can depend on your parameter. Now, in this case, the degree of the polynomial was just my parameter itself, but it can be any function of my parameter. So if I have an algorithm whose runtime is, for example, O(n) to the power of 2K. This is also XP. Okay? Because again, if I can somehow guarantee you that in all the inputs that you're going to see K is small, then no matter what this function is, it's going to be a constant. And then n to the power of that constant is just going to be polynomial time. Okay. But now, as you see, this is not very nice. So if I have an algorithm that, for example, looks like this, that's not really going to work for any real world inputs, right? So maybe I prefer to have an algorithm where the degree of this polynomial does not depend on K. So let's see if we can find an algorithm like that for vertex cover. Okay. I want to find an algorithm whose runtime, well, can still depend on K and N, but I don't want the degree to depend on K. So here's a simple idea. Let me just remove the solution that I already had here. Okay, so let's say this is my graph. And let's say I just arbitrarily take one edge of my graph. So for example, I choose this edge. Now, if I choose this edge, then what do I know about this edge? I know that it has to be covered by my vertex cover. So I have to either include this side of the edge into my vertex cover, or I have to include this side of the edge into my vertex cover. Okay? So I can just recursively try both. So I say I want to solve this problem, and let's just write the parameter here. So I want to find the vertex cover of size k for this graph. I just take this edge, and I say that either this side should be in my vertex cover or this side. So there are two cases. Now, if I put this vertex in my vertex cover, then it already covers all of these three edges here, right? So I can just create a graph with the rest of the edges. So it would be something like this. And of course, I have this one vertex here as well, right? So I remove this vertex. I remove all the edges that were covered by this vertex. And now I have to cover the rest of this thing, this graph. But now I have to cover this one with k minus 1 vertices. So my parameter decreased from k to k minus 1. Now, on the other hand, if I take this vertex into my vertex cover, then it's a similar situation. It covers these three edges. And then I have to look at the rest of my graph. So my graph would then look something like this. Right? And again, I have to cover this one with k minus 1. Okay? So if I want to write this in a more general way, this is how my recursion works. I have some graph G and some parameter K, which is the maximum size that I can have for my vertex cover. And I'm taking this edge, let's say this was between vertices U and V. And then I'm saying that I have to consider two cases. Either I have to remove the vertex U and all of its neighboring edges, and then my parameter becomes k minus 1, or I have to remove the vertex V, and my parameter becomes k minus 1. Now, I just continue this recursion. So at this point, I will just choose another edge, and then I will just have two cases where I have some other graph and parameter k minus 2 in all of them. And here I will do the same. Now, when does this recursion end? So this recursion ends either if I cannot find any edges, which means that I've already covered everything. In that case, I was just successful. I found my vertex cover. Or it might be that as I'm just going down, the value of k is going down, and then the value of k at some point becomes 0. And if the value of k becomes 0, I can't take any more vertices, but I have edges left. So at that point, I can say the answer is no. But how deep can this recurrence tree go? It can go at most k steps down. It can have at most k levels, because I'm starting with k here and the value is decreasing. So the number of vertices in this tree is at most 2 to the power of k. So my runtime is going to be 2 to the power of k times the amount of time that I spent at each one of these vertices. So how much time did I spend to go from here to here? Well, I just had to choose an edge, right? But then I had to create 2 copies of my graph. So that copying process is going to take n plus m time, right? So my overall runtime is 2 to the k times n plus m. Now, this is much better than the previous runtime that we had. So remember, our previous runtime was n to the power of k times n. Now, you see here the dependence on k was in the degree of the polynomial. But now with this recursive algorithm, I have a linear time algorithm anyway, and the dependence on k is just in the constant factor. So if k is, for example, 10, here I get an algorithm whose runtime is 2 to the power of 10 times something linear. So yes, it has a huge constant factor, but at the end of the day, it's linear. Whereas here, I would take an algorithm that has a runtime of n to the power of 10 times n, which is awful. So we prefer algorithms of this type, and we should have a name for that. So the name that we use for algorithms of this type is FPT. And okay, let me maybe erase this part. Okay, so the name we have is FPT, and it stands for fixed parameter tractable. So a language, a parameterized language L is in FPT if there is an algorithm let's call that algorithm A that solves L or decides L. And now again, I have to talk about the runtime. So if I run this algorithm A with some output X and some parameter K, I want the runtime to be at most a polynomial in the size of the input, which is a polynomial in X, right? So I want it to be X to the power of some constant. But I also want it to be able to depend on K, but the dependence in K should only be in the constant factor. So my runtime should be X to the power of some constant times some function of K. Okay? And again, I don't care what this function is. Normally, well, sometimes in some books you see that they say the function has to be at least computable. So we don't want to have a non-computable function here, but that doesn't really happen for us. So I'm just going to define it like this. So now again, since this function can be any arbitrary function, I can, for example, have something like this. I can have an algorithm that takes n4 times, again, 2 to the power of 2 to the power of 2 to the power of k, right? But this is much better than the previous case anyway, because this is a huge constant, but it's a constant. And it's not appearing in the degree of the polynomial. It's just appearing as a constant factor. So even though you can also come up with FPT algorithms that are not really useful in the real world, this is a better definition than XP, and we usually try to find algorithms that are FPT. Okay. So this technique that I showed you here, this is usually called branching. That's just another name for recursion. So we say we're doing branching whenever we apply a technique like this. And usually the idea is that in my branching, as I go down this branching tree, my parameter decreases, or something dependent on my parameter decreases, so that I can say that the depth of this tree is going to be a function of my parameter. And then I spend polynomial time at every node of the tree. So I can say overall, I have an FPT algorithm. Okay. So let me give you another example of this. And this is called the problem of feedback vertex set in tournaments. Now, a tournament is basically just a complete graph in which you just add directions to each one of the edges. Okay? So a tournament on n vertices. Let's say my vertices are just 1, 2 to n. Is a graph G, where again my vertices are just this set, such that for any two vertices I and j, either I have ij in my edges, so ij is in E, or ji is in E. And actually, I want this to be an exclusive form. Okay, so any two pair of vertices, either I have an edge from I to j or from j to I, but not both. So this is a tournament. Now, what is a feedback vertex set? A feedback vertex set, or I just write it FVS, in a graph G is just a set of vertices. So it's a set, let's call it F, subset of my vertices, such that if I remove these vertices from my graph, then I will no longer have any cycles in the graph. Such that if I take G and I remove F from it, then I have no cycles. Okay? So the way you can think about this is that when we were doing vertex cover, we wanted to remove some vertices so that all the edges are removed. Now here I want to remove some vertices so that all the cycles are removed, so that I no longer have a cycle in my graph. And now I'm talking about a directed graph, of course. Okay. Now, of course, the problem is going to be similar to before. So I give you a tournament, and I also give you some number k. And I ask you, does this tournament have a feedback vertex set of size at most k? So can I remove at most k vertices from my tournament so that there are no cycles in the tournament anymore? So it becomes acyclic. Now, you see previously when we were talking about vertex cover, I would just take an edge and I would say that this edge has to be covered. And there are two cases. Either I have to put this end of the edge into my solution or this other end. So I could have something like this, where I had a branching factor of 2. Each time I branched into 2 different ways. But now I'm talking about cycles. So if I want to get rid of a cycle, it's this one. So let's say that I take my graph G and I find some cycle in it. And this is a directed graph, so I will have a directed cycle. Right? Now I know that I don't want to have any solution, any cycles in my solution. So I have to get rid of at least one of the vertices on this cycle. But the problem is, if I do that, then I have n possible choices for that, because in the worst case, my cycle can just have length n. And then here, when I'm doing this branching, every time I'm not going to branch into 2 parts, I'm going to branch into n parts. And then my overall runtime would become n to the power of k. Right? But that's fine. That gives me an XP algorithm, but it doesn't give me an FPT algorithm. So in order to get an FPT algorithm, I have to make sure that my branching factor is limited. Okay, now let's go back to this cycle that we had found here. And let's take 2 of its vertices. So for example, let's say I want to look at this one and this one. Let's call this one I, let's call this one J. Now I know that my input was a tournament. So there should be an edge between either I and J or J and I. Now, if there is an edge from I to J, then I actually have a shorter cycle here. Right? On the other hand, if there is an edge from j to I, then I have a shorter cycle on this side, right? So in every case, as long as my cycle has more than 3 vertices in it, I can take 2 vertices that are not neighbors in my cycle, and then I can use them to create a smaller cycle. So basically, the lemma that I just proved here is that a tournament has a directed cycle if and only if it has a directed cycle of length 3. So I can now just focus on triangles, on cycles of length 3. So my algorithm every time is that I take my graph, I find the cycle. Then I just try to make this cycle smaller and smaller by adding these internal arcs. And at some point, I get to a cycle that has only 3 vertices. So let's say I have now a cycle that just has 3 vertices. Now I use the same idea that I had for vertex cover. I say that this cycle has to be eliminated, so I have to take at least one of these 3 vertices into my feedback vertex set. And now I just try every possibility. I just say I either take this one or this one or this one, and in any case, I would just recursively try to solve my problem. So here, my solution would look very similar, except that each time I'm creating 3 new instances. So I had U, V, let's say the vertices are U, V, and W. So I have to take G minus W and K minus 1 here as well. And here again, I will have 3 branches. Here I will have 3 branches and so on. So now I can again do the same analysis that I was doing for vertex cover. I can say that the depth of this graph is K, because as I'm going down, every level that I'm going down, the value of K is decreasing. So the number of nodes is going to be 3 to the power of K, because my branching factor is 3. But how much time do I spend at every node? So how much time do I spend to find a triangle? If I give you a graph and you're supposed to just give me a triangle in that graph, how much time do you need for that? So I claim that I can do it in time n plus m. How? Well, I just take some vertex and I start a DFS. And I just continue in here until I find the cycle. And then when I find the cycle in my DFS, I just apply this algorithm. Every time, as long as my cycle is has at least 4 vertices, I just take 2 vertices that are not adjacent and use that to shorten my cycle. So the runtime is just the runtime of a DFS. It's n plus n. Okay, so as you see, now we could do kind of a naive branching, and that would give us n to the power of k times n plus m. But we could also do this better branching here, and it gave us 3 to the power of k times n plus m. So this is an FPT algorithm. This is just an XP algorithm. Of course, if every FPT algorithm is also an XP algorithm, but we prefer FPT. But another point here is that this XP algorithm actually doesn't use the fact that we have a tournament. So this would just work for the feedback vertex set problem in a general graph. Whereas this one used the assumption of the graph being a tournament. Okay. So now I want to show you another technique. And for that, let's go back again to our vertex cover problem. So vertex cover is just our favorite problem for parameterized algorithms. Okay, so these are the algorithms that I already have for vertex cover, and these are the runtimes. But let's see if I can solve the vertex cover problem in a different manner. And you will see that as I write my problems, I also explicitly say what the parameter is. So I write it like this: vertex cover parameterized by solution size. So this means that my parameter k is the size of my solution, the size of the vertex cover. And then later on in this module, we will actually use different parameters as well. Okay, but let's recap what the problem is. I have a graph G. I want to remove some vertices so that all the edges are removed. Okay, and I want to remove at most k vertices, and I know that k is a small number. So can I come up maybe with some heuristics that would just help me with this task? So here's a simple question. Let's say I have a vertex that has degree 0. So this is an isolated vertex. Does it make sense to have this vertex in my vertex cover? Of course not, because it doesn't cover any edges. So if I have a vertex of degree 0, I can just remove that vertex from my graph and nothing changes. The solution remains the same. So the way I write this is that I call it a reduction rule, or RR. And my first rule is that if some vertex V has degree 0, then take your instance, which was GK, and instead of solving GK, just solve G minus this vertex and K. Right? And I say that this is a safe rule, and by that I mean that the solution to this problem and the solution to this problem are the same. Either they're both yes or they're both no. So this is my first trivial reduction rule. Now let's think about the degrees a little bit more. Let's say that now I have some vertex, and that vertex has degree 1. So let's say I have this vertex V, and it's only connected to one other vertex. And then the rest of the graph is here. Right? Does it make sense to have this vertex, this V, in my vertex cover? Again, the answer is no, because if you give me a vertex cover that contains this V, I can then just remove V from the vertex cover and add its neighbor to the vertex cover. And the neighbor is a better choice because it covers everything that V used to cover, which is this edge, but it also covers a bunch of other edges. So in this case, it also makes sense to just remove V from my vertex cover and put U in my vertex cover. So this is my reduction rule 2. If the degree of V is 1 and U is the only other vertex that is connected to V, then I take my instance, which is GK, and I just turn it to G minus U minus V and K minus 1. Okay? Now, why did this happen? Because, well, I'm saying that I don't want to put V in my vertex cover, but then I definitely have to put U in my vertex cover. So after I put U in my vertex cover, U and V and all of the edges that are connected to them are already covered, so I can remove them from my graph. And now I have K minus 1 more vertices that I can put into my vertex cover. Okay, nice. Now let's look at it from the other way. And let's say that I have a vertex that has a very large degree. So let's say I have my vertex V, and it's connected to a lot of other vertices. Okay, let's take the most extreme case. Let's say that V is connected to every other vertex. So degree of V is n minus 1. Should I put V in my vertex cover? So I have to cover all of these edges. If I don't put V in my vertex cover, then I'm forced to put all of its neighbors in my vertex cover. But I can only have a vertex cover of size K. So if the number of neighbors is more than K, then my only choice is to put V itself into the vertex cover because I can't choose to put all of its neighbors. Okay, so this is my third rule. And my third rule is that if the degree of V is larger than K, then I know that I have to take V. So from GK, I go to G minus V and K minus 1. Because I took V into my vertex cover, and now I have K minus 1 more vertices that I can reach. Okay. So now here's my algorithm. I just try to apply these rules as many times as possible. So as long as I can apply one of these rules on my graph, I just apply it. And what do these rules do? They just make the graph smaller and smaller, right? So this rule is removing one vertex. This rule is removing two vertices. This one is removing one vertex. So if I just apply these rules as many times as I can, I expect that my graph gets smaller. But I have to prove that. I have to prove how small my graph gets. Okay. So what can I say about the degrees after I have applied these rules exhaustively, after I have applied these rules as many times as possible? I know that I no longer have a vertex of degree 0 because this rule would have removed it. I know I don't have a vertex of degree 1 because this rule would have removed it. And I also know that I don't have a vertex of degree greater than K because the last rule would remove it. So after I apply all these rules, I know that for every vertex, the degree of that vertex is between 2 and K. Okay, nice. So I started with an arbitrary graph, and now I have a graph in which I have some nice properties. Now I got these properties kind of for free. I just applied these rules, and it takes polynomial time to apply these rules. And I realized that my degrees are now between 2 and K. But what does this tell me about the number of edges in my graph? Now, here's the thing. Suppose that the answer is yes. Suppose that my graph has a vertex cover of size K. Right? So I should be able to choose K vertices that cover all of my edges. But every vertex can cover at most K edges. So if I have more than K squared edges at this point, I know that the answer is definitely no. Because there is no way I can choose K vertices that cover more than K squared edges. So at this point, after I applied all of these rules as many times as possible, I say if the number of edges is more than K squared, then just return no or return 0. There is no vertex cover of size K. But now this makes my life much easier, right? Because if I don't return no, then that means I have at most K squared edges. So now my whole graph, which had M edges, can now have at most K squared edges. So the number of edges in my graph is now dependent only on this small parameter K. So I have a really small graph. Okay, so at this point, I know that the number of edges is at most K squared. But if I have at most K squared edges, what can I say about the number of vertices? How many vertices can I have? So if you have a graph and the graph has K squared edges, what is the maximum number of vertices? Well, you can have a case like this, right? So you can have a bunch of completely separate edges. And if you have K squared edges, then you have 2K squared vertices. And you can't have more than that. But actually, we can find an even better bound here. I know that the degree of every vertex is between 2 and K. So every vertex has degree at least 2. Okay, what do I know about the sum of degrees? So let's take the sum of the degrees of all of my vertices. So of course, in every graph, the sum of degrees is twice the number of edges, right? And the number of edges is K squared. So the sum of degrees is at most 2K squared. But on the other hand, I know that every vertex has a degree of at least 2. So this sum is at least twice the number of vertices, right? So twice the number of vertices is at most 2k squared. So the number of vertices is at most k squared. So here's the part where it gets really interesting. So I started with a general graph. I kept applying these rules. And I ended up with a graph that has at most k squared vertices and k squared edges. So now in this graph that has k squared vertices and k squared edges, I can just do a brute force, because anything I do on this graph, its runtime will only depend on k, and I can depend on k in any way that I like, right? So I can just do the brute force algorithm where I would just take k vertices out of the k squared possible vertices, and I would just check if they cover all the edges. That's the runtime of the brute force algorithm. So my overall runtime is the runtime of this brute force algorithm, but now I'm applying the brute force algorithm only on a small graph, plus the time it takes for me to get from my original graph to this small graph. So the time it takes for me to apply these rules. Okay, how much time does this take? If you want to apply these rules as many times as possible until you can no longer apply them. Actually, you can do all of that in linear time as well, right? Because all of these rules were only dependent on the degrees. So just keep track of the degrees and then just apply the rules. So each time you find a vertex of degree 0, you remove it, and that's it. Each time you find a vertex of degree 1, you remove it, you decrease the degree of its neighbor. And for this one, it's also the same. It's just that you're finding a vertex of high degree. So this part is just going to take n plus n. So now this is my runtime. And this is much better than the previous one, right? Because remember, previously, what were the other algorithms that I had? I had n to the power of k times m, which was the first naive algorithm. Then I had the branching algorithm, which was 2 to the power of k times n plus m. But now I have this. So this part is only dependent on k, and it's not being multiplied in this one. It's just additive, right? So this is even better. So now I have an even better runtime than this one. But can I do even better than this? Well, yes. Why should I apply this naive algorithm in the end? I can just apply my branching algorithm in the end. So I can first use these rules to make my graph as small as possible. And then after I get to a point where I have at most k squared vertices and k squared edges, I say at that point, I apply the branching algorithm. So then my runtime would be O. Well, I spent n plus m time to get to the small graph. But the small graph, I'm then applying this algorithm to it. So it would be 2 to the power of k. But n and m are both k squared, 2k squared. So 2 to the power of k times k squared plus n plus n. Now you see just a kind of a clever combination of the ideas from both sides really gives us a much better runtime. Okay, so this idea that you saw here, the idea of starting with some input to your program and then trying to make it smaller and smaller until the size of your inputs just becomes a function of your parameter, this is called kernelization. And we will see many more examples of this in the coming lectures. So this is kernelization. And yeah, that small graph is called the kernel, because the idea is that you have like a huge problem, but the hardness is really just all in a small kernel. So you get that kernel, you solve the kernel, that's it. That's the kernelization idea. I talked about the branching idea, but one final point here. So here, when I was finding a bound on the number of vertices, it really helped me that the degree of every vertex was at least 2. But can I also maybe have a rule that gets rid of vertices of degree 2 so that I can say the degree of every vertex is, let's say, at least 3? Because if I can come up with a rule like that, then this kernel, the small graph, really becomes even smaller. And then my overall runtime would decrease. One last point that I want you to see here is that it's really important what you choose as your parameter. So in the examples that we saw today, I always chose the solution size as my parameter. But that wasn't really part of the definition. When I was talking about a parameterized language, or when I was talking about XP and FPT, I just said that the parameter is something that is given in the input. It doesn't have to be the size of the desired output. It can be any other thing. So I could parameterize, for example, vertex cover by degree. Maybe I could say that I know that in all of the real world instances where I need to solve vertex cover, all the graphs that I have are going to have a degree of at most D. And then I could try to find an algorithm that was FPT with respect to this new parameter, with respect to D. And if you change the parameter, basically you're changing the whole problem. So it's not the same problem anymore as soon as you change the parameter, and the same algorithms would generally not work. So we will see an example of this in the future sessions. And the example is actually the example of a clique. So if I give you a graph and I ask you, does this graph have a clique of size k? And if the parameter is the size of the clique, if the parameter is k itself, then we will see that we cannot have an FPT algorithm for that. But if I say I give you a graph, I also guarantee that the degree of every vertex is at most D. And I ask you, does this graph have a clique of size k? But now I say that D, the degree, the maximum degree among all the vertices, that's going to be your parameter. Then you can easily find an FPT algorithm. Right? So if I know that all of my vertices have small degree, I can just take a particular vertex and say this vertex is either going to be in my clique or not. If this vertex is not in my clique, I just remove it. If this vertex is in my clique, then all the other elements of the clique should be neighbors of this vertex. So I can just look into the neighbors of this vertex, but I'm parameterizing by D, and the number of neighbors is at most D, so I immediately have a kernel there. Right? So as you see, it really matters what you parameterize by. And if you change the parameters, you can actually change the hardness of the problem. So that's why whenever from now on I write about the problem, I write the name of the problem, and then I also write what the parameter is. So I would never just talk about vertex cover anymore. I would talk about vertex cover parameterized by solution size. Okay, I'll see you on Thursday.